So I got something pretty cool in the mail today. This is a brushless DC motor. These things are cool because they're powerful, efficient, and they require very little maintenance. Since these things are so good, they're starting to show up in a lot of robotics. You can see 3 per leg in the MIT Mini Cheetah, and that thing is crazy. It can do backflips, it's very agile and fast. And also one of my favorite YouTubers, James Brutton, is using them for a new version of his quadrupedal robot, OpenDog. So naturally I wanted to experiment with them myself. However, all these benefits of the motor come at a slight cost. They're fairly difficult to control. You can see there are 3 wires going to the motor. And if we apply a voltage to any 2 of them, the motor just jumps around. It doesn't spin like we would expect it to. That's because these types of motors require a special circuit to control them called an electronic speed controller. This is a typical ESC. It has 3 outputs for the motor, 2 inputs for power, and 1 more input which we can drive to tell it how fast we want the motor to spin. These work great for things like quadcopters where you just want to spin the motor very quickly. But for robotics, I want very accurate and precise control over the output of the motor. I want to spin it quickly, but also very slowly and smoothly. So, using my vast and expansive knowledge of electronics and circuitry, I actually don't know what I'm doing, send help. I will create my own electronic speed controller and train it with reinforcement learning to control the motor. First, we should understand the motor a little more with a diagram. Here I redrew the small portion circled in red on the motor. Every BLDC consists of 2 main parts, the rotor and the stator. The rotor rotates and the stator stays still. You can see that the rotor is on the outside of my motor, and so it's called an outrunner, and these typically have more torque than their in-runner counterparts. Now if we power this coil with current going in this direction, we will effectively turn it into a magnet with its north pole up here at the top. Now, similar poles repel while opposite poles attract, and so you see we generated a torque going counterclockwise. Similarly, if we power it with the current going in the other direction, the south pole will now be at the top, and opposite poles attract, like poles repel, and our torque is now going in the other direction. So now we're spinning the motor clockwise. To predict where the north pole will be, you can take your right hand, wrap your fingers around the direction that the current is flowing, and your thumb will point in the direction of the north pole. Now that we have a basic idea of how the motor works, let's simulate it and see if it's possible to control it with reinforcement learning. Okay, so here's my simulation. I wrote it in Python and I used Jupyter Notebook to run the code in these cells so I can kind of interact with it and run blocks of code one at a time. Now on the right you can see this diagram. It's a simplified version of the real motor. It has 2 rotor magnets, a north and a south pole, and it has 3 stator magnets which we can control. So we can have them unpowered like C, we can have them be a north pole like A, or a south pole like B. Now you can see right now the rotor is at a certain angle, and that makes sense because this north pole is attracting this south pole and this south pole is attracting this north pole, and so the rotor is trying to align with the stator. Now if we want to rotate the rotor to a certain angle, we have to power the stator in the right way. You can see there are 6 main ways we can power the stator to get 6 different angles for the rotor in this diagram. So let's try to do the first one. Let's just get to 30 degrees. And you can see now A is the north pole and C is the south pole, and so the rotor is lined up right with them. Let's do 90 degrees. And you can see my simulation, I can step it so we have some time, and the rotor has some inertia, so it takes some time to get there, but eventually it does. And let's look at the stator for 90 degrees. So C is the south pole, B is the north pole, A is unpowered, and so it makes sense these opposite poles are attracting each other, and so the rotor is pretty much at 90 degrees. We can do 150 degrees, 210 degrees, 270, and 330. Now, if I just run those in order, one after the other, you can see we can make the rotor spin. And if I speed up the time that I switch the states of the stator, you can see we can kind of make the rotor spin smoothly. Now if I reverse the order that I power the stator, you can see we can reverse the direction of rotation of the rotor. And so this is our basic simulation of a BLDC motor. Now what I want to do with this is reach a target angle. So in this code block here, I tried to just drive the motor forward if it was below the target angle and backward if it was above the target angle. And you can see it kind of works. You know, it's a little jumpy though, right? Like it has to pass the target angle to start changing direction. And that's because the motor doesn't have any idea of where its current angle is. So it just has to drive in one direction until it passes the target angle, and then I start driving it in the other direction. It's not aware of where its actual angle is. Finally, to make sure that I can drive the motor between those 6 angles we know we can already reach, I made this function which lets us get between 2 states, 2 stator configurations, by just turning one on very quickly and then turning the other one on, and then turning the first one on and then turning the other one on. So right now we're between states 2 and 3, and so that should correspond with angles 0, 1, 150 and 210. And we can go between any 2 states. So let's just go between 0 and 1. So this kind of proves that we can reach any angle in the entire rotation of the rotor, not just those 6
Okay, we get it. But can we just do this with machine learning like we plan to, myself? Okay, good. So of course we can do this with machine learning, and we're going to use something called Q-learning in this video. So Q-learning is an algorithm. It's just a set of rules to follow to perform some calculation. It's a part of reinforcement learning, which is an area of machine learning concerned with algorithms designed to maximize some reward. And what it does is it learns the value of taking actions A from states S. So this is a typical diagram of a Q-learning system. We have our Q-learning algorithm up top, and then we have our motor simulation down below, and this could also be a real-world physical robot. So Q-learning works by choosing an action, which we then feed into our simulation. Our simulation runs and returns a reward and a new state. This goes back into the Q-learning algorithm and informs it about how good that action was that it just took. So for our case, an action is a configuration of the stator coils. So we can have coil A be unpowered, we can have coil B be a north pole, and coil C be a south pole. That's one of our possible actions. We then feed that action into the simulation, which then returns a change in the motor's velocity due to executing that action, and also a new state, the angle of the motor, say it ended up at 80 degrees. By defining the reward to be the change in the motor's velocity, we're basically telling the system that a higher change in the motor's velocity is desirable, and so this thing is going to try to maximize the change in the motor's velocity, which just means make it spin very quickly. So to answer how Q-learning learns the value of an action, I thought we would use a small toy example. So we got this dude, he's on a cliff, and he's hungry, and he's happy, and he sees a magical floating bar of chocolate. But the chocolate is floating over a giant pit of fire. So the dude is in a certain state, and we'll call that state being on the cliff. Okay? And now the action is, should he take the chocolate or not? So he, of course, decides to take the chocolate, and he jumps off the cliff. And he's kind of just floating in midair here. Let's just clean him up quickly. So he's floating. He took the action, but he hasn't transitioned yet to the new state. So to do that, we have to run our simulation, and he's not going to be very happy, because when we run the simulation, he ends up in a pile of melted chocolate, and he's still a little crispy. There's still a little fire going on too. So he's not very happy. And so when he took the chocolate, he got a reward, a positive reward, but ending up in this new state, it's very bad. It's a crispy state. He doesn't like where he ended up. So what's the value of taking the chocolate? That's the question we have to answer. Now, to answer that, we just use this simple looking, whoa, that is not a simple looking formula. Let's just run away from that right now. We will come back to that. Let's just use this toy example a little more, and then we'll go look at that crazy looking formula. So at a high level, taking the chocolate, we didn't know what it was before. We took it, we got a reward of 10, but we ended up in a new state, the crispy state, and it was bad, so that had a value of minus 100. And so the value of taking the chocolate is probably something like the sum of the two, so maybe negative 90, or not that good. All right, so let's go back to that scary expression now. I think we're ready. So this is the TD update, or temporal difference update, and this is the way that we learn the value of taking an action given we're in some state. You can think of Q of SA as the value of taking action A from state S. That's like the value of taking the chocolate while we're on the cliff. The arrow just means we're assigning a new value to this, and that new value is based off of the old value, because we just want to change the value a little bit, plus alpha times this whole expression to the right. Now, alpha is something called the learning rate, and it's just how fast that we update the value of Q of SA. For this example, let's just make it be 0.3. Next, we have the reward, which was 10 for eating the chocolate, plus this gamma, or discount factor, and that's how much we want to discount the value of future states. If we want to ignore the value of future states, we could set that to be 0. But if we care about the value of where we end up, we would want this to be something non-zero. So let's just make that 0.9. And then we have Q of S prime A star. S prime is just the next state that we end up in, and then A star is the best action from that state. So Q of S prime A star is the value of the best action from the next state. In our case, that was minus 100. Finally, we just take the difference with the old value, which was 0 in our case. And whew, that's the entire update. So now it's just algebra. So we just plug these values in, and you can see that the value of taking the chocolate in this case is minus 24. Not that good. Okay, so now let's run this process on our motor. So our motor is going to start in some random state S, and get out of here, Spotify. That state, let's say it's something like 0 degrees, so I'll just draw our little motor here, 0 degrees. And we're going to have a bunch of Q values for that state. We're not going to know them yet, so we'll start them out at 0. And then we choose a random action. Maybe A is unpowered, B is a north pole, C is a south pole. And by choosing that action, we're going to get a reward from our simulation. And we're also going to end up in a new state, S prime. And it could turn out that S prime has really crappy actions. They're all negative. So it's making the motor spin in the other direction. And so we want to update the Q value that we just took based off of the reward and the new state that we got to. So it's basically just substitution. We're trying to update this value here. So we have to substitute in our old value, which was 0. And then a learning rate, let's just make it 1. And then the reward was 10. Let's just choose a discount factor of 0.2. And then the value, the best action at the next state, S prime, is minus 4. So that's going to be our A star.
And so the best q value from s prime is just -4. And then we subtract our old value, and so now it's just algebra. So our new q value is 9.2. So the value of taking this action, A none, B north pole, C south pole, is a 9.2. And that makes sense. You know, we got an immediate reward of 10, so it looked like our velocity was going to be able to change a lot. But we end up in a state where we can't change the velocity to be positive, and so we want to factor that in. And so the value of taking that action is not 10, but something slightly less than 10. So why do we choose that particular action? Well, unfortunately, there's one more Greek letter we have to know about, and that is epsilon. So epsilon is a number, and it represents how much exploration your agent is going to do. So for this example, we're in state 0. There are 6 actions we can take, and each one has a q value. We're going to choose the actions randomly, but we're going to favor the best action a little bit more than the others. To do this, I assign a probability to each one based off of epsilon. You can see all the actions get epsilon over 6, but the best action also gets a +1 minus epsilon added on. The best way to understand this is to just choose a value for epsilon and see what probabilities we get. So if epsilon is 1, we're going to get 1, 6, 1, 6, 1, 6, 1, 6, plus 1, minus 1, which is just 1, 6, and 1, 6. So you can see everything is equally likely if epsilon is set to 1. And we call this full exploration. Now, if epsilon is 0, we'll plug that in. So everything's going to have a 0. This is going to be 0 plus 1 minus 0. And then the last one is going to be 0. And you can see we're assigning all probability to the best action. So this is called full exploitation. We're not exploring anymore. We're just choosing the best action. Typically, you set epsilon to 0 once you've fully explored your environment and you know the value of each action. So we run all of this complicated machinery, and this is what we get, just a bunch of numbers. And what this is just a mapping from states to the values of the actions you can take from those states. So you see 0.0 on the left there, that's a motor angle. And then you see a list of values, and those are the q values of each of the actions you can take from that angle of the motor. So to use this, we just look at the angle of the motor, and then we choose the action that has the highest q value. And that will lead us to spinning the motor faster. Okay, so after all of that, does it actually work? Well, I have the code here, and I'm just going to run it and train it. The red graph is the reward. It looks like it did something, so it's done training. We can look at the q values. This is just a dictionary of all those q values. And we can focus in on the 0.0 state. So these are the q values for the motor at the 0th angle. And it looks like the second action is the best action to take here because it has the highest q value. So now let's just actually run the motor. So given the motor's angle, this will choose the best action, the one with the highest q value. And you can see that it works. It's making the motor spin. And that's all I've ever wanted in my life, is to make this motor spin. But hold on to your papers because it's going to get crazy. What do you think would happen if we choose the worst action? If you think the best action makes it spin counterclockwise, the worst action probably does something else, makes it spin in the other direction. So we actually get to spin the motor in both directions, even though we only learned to spin it in one direction. We just choose the best actions if we want to spin it counterclockwise and the worst actions if we want to spin it clockwise. Spinning the motor is fun, but I wanted to drive it to a target angle. So I just compare the angle of the motor and the target angle, and based on that I can drive the motor in either direction to reach the target. So let's look at that. Go baby go! Oh, and it reached it. So once it reaches the target angle, it's surprisingly good at staying right on it, regardless of how fast or slow that target angle is. So I would call this a success, and this success didn't come easy. You know, I tried a whole bunch of different strategies to get this thing to train. I I tried this thing called evolution strategies. That failed completely. I tried just choosing the best weights. I was taking a linear combination of the features of the motor, blah, blah, blah. That didn't work. I tried a whole deep learning, reinforcement learning package, and I couldn't get that to work. I also tried various state representations, like the angle of the motor and the direction I wanted to spin, but that just doubled the amount of things that I needed to learn. So I think moving forward to the physical motor, this Q-learning solution that I've come upon will work fine. Yeah, right. I mean, whenever you take things to the physical world, they all blow up. But if you like explosions, then blow up that subscribe button so you don't miss the next video. If you like this video, smash that like button, hit the bell, you know all this stuff. I'm starting to make videos every month now, and it's really fun. So I hope you guys enjoyed this. Thanks for watching, and I'll see you in the next video.